In this lecture, we are going to start discussing modern RNN units. You may have heard of these already, so I'll just tell you right now what they are: the LSTM and the GRU. LSTM stands for Long Short-Term Memory, and GRU stands for Gated Recurrent Unit. They are both essentially the same thing, with the GRU meant to be a more simplified and efficient version of the LSTM. This lecture will discuss why the LSTM and GRU are needed in the first place, when the simple RNN seems pretty good already. We'll also look at the underlying equations for the LSTM and GRU, and importantly, a convenient perspective for looking at them. One mistake a lot of beginners make is that they see a bunch of equations and they get very intimidated. They think, what the heck is this? Just a bunch of equations? What do I do with this? So hopefully this lecture will take you from that lazy beginner's mindset to how a proper machine learning engineer would think about LSTMs and GRUs. First, we need to discuss why we have these fancy new recurrent units in the first place. Why is a simple RNN unit not good enough? To understand this, we have to go back to the vanishing gradient problem. As with our RNN, we can represent the output prediction y hat of big T as a function of the inputs x1, x2, all the way up to xt. Once we do this, we can see that it's just a really big composite function. Now suppose we want to take the derivative with respect to wxh. We can see that wxh appears several times in this equation. Now the actual derivatives themselves and how to find them are not what we have to consider here. But what is important is which derivatives are going to show up. Well, if wxh appears multiplied by x of t, then we're going to have to find the derivative of wxh times x of t at some point in our expression for the gradient of wxh. It should be clear that wxh appears in front of all the x's for every time step. So ultimately, all of these single derivatives are going to appear somewhere in our expression for the gradient of our cost with respect to wxh. But another thing that's important to consider is how deeply nested each of these terms is with respect to y hat of big T. What is clear is that the term involving x1 is the most deeply nested. The term involving x2 is the second most deeply nested, and so on. Now, what do we remember about the derivative of composite functions from our theory of RNNs? Well, we know that composite functions turn into multiplication in the gradient. This is due to the chain rule of calculus. Therefore, the more deeply nested you are, the more terms you have to multiply by when you're finding the gradient. In other words, RNNs are particularly vulnerable to the vanishing gradient problem. The farther back in the sequence the input is, the more vulnerable it is to the effects of the vanishing gradient. This is why it's often said that RNNs have problems learning long-term dependencies. The RNN simply can't learn from inputs that are too far back. So how does the vanishing gradient problem manifest in actual machine learning applications? Let's suppose we're doing natural language processing and we would like to extract some information about a document. So to give you a concrete example, suppose our AI is reading the Wikipedia page about Albert Einstein. It's read the entire page. Now you ask your AI, on what day was Albert Einstein born? Unfortunately, a simple RNN would not be able to answer this, even though this information appears in the article. The problem is, it appeared at the beginning of the article, so by the end of the article, the simple RNN has simply forgotten what it had read earlier. Now you might think, aha, I have the solution to this vanishing gradient problem. It is to use ReLUs. Unfortunately, with RNNs, things aren't so simple. Of course, you can always try to use ReLUs in your RNNs and verify experimentally what the results are. But in deep learning, we found that the most effective way of dealing with this problem is to use entirely different units, namely the LSTM and the GRU. One interesting historical fact is that the LSTM was created a very long time ago, 1997. This is more than a decade before deep learning was even called deep learning. So this is why I always say to people, research interesting ideas. Don't just go through your career chasing what is popular. By doing that, you are like a hamster running on a spinning wheel going nowhere. If you're only chasing popular mainstream ideas, you would have never come across this idea of LSTMs. It's more than a decade old, part of a field that nobody even cares about. Do what is interesting, not what is popular. Now, the LSTM is an extremely complex unit. The GRU was invented more recently, in 2014, but it uses a lot of the same ideas. So I always like to start with the GRU so that you can learn the principles in a simpler setting and then go back to the LSTM. So what is the gated recurrent unit? First, let's start with the basic principle from a simple RNN. We still want to have some hidden state at time t, h of t. This hidden state will still depend on x of t, the current input, and h of t minus 1, the previous hidden state. The only thing that will change is how h of t is calculated. Now, there's a little bit of a debate on how to present the GRU and LSTM. Is it more useful to look at the equations, or is it more useful to look at diagrams? Now, if you are a beginner, you might automatically say, pictures are the best for learning. Unfortunately for you, that's not what we are going to do. A lot of poorly written blogs that all copy from each other use these same diagrams as if they were self-explanatory. You look at this picture, and all of a sudden, bam, you understand LSTMs and GRUs. Personally, I find this doesn't work for me. I know that other prominent lecturers feel the same way. Of course, if you find these pictures useful, you are welcome to look at them and try to make sense of them. But for me, and many others I know, it's actually the equations which are most useful. That might seem backwards to a beginner who is very terrified of math, but hopefully you are past that point right now. I promise you that there's nothing here that we haven't seen before. Okay, so enough chit-chat. Where's the GRU? Well, here are the equations for the GRU. To sort of give you some perspective on this, I've also included the equation for a simple recurrent unit so that you can compare the complexity of the two. The simple recurrent unit is essentially just one line. H of t depends on x of t and h of t minus 1. The GRU is 3 lines because we have to calculate 3 different things. First, we calculate z of t, which is called the update gate vector. Second, we calculate r of t, which is called the reset gate vector. And finally, we calculate h of t, which is the hidden state vector, which is, as with the simple recurrent unit, what gets passed on to the next layer in the neural network. So let's analyze these equations so that we can make sense of the GRU. First, it's important to discuss shapes. You want some visualization of the objects we're dealing with. Well, it's helpful to know that all of these new vectors are just vectors of size m, the same size as h of t. As always, this is a hyperparameter, so you can choose how many features the hidden layer should have. This also implies the shape of all these weights. If a weight is going from x of t to one of the gate vectors, then it must be of size d by m. If a weight is going from h of t minus 1 to one of the gate vectors, then it must be of size m by m. And of course, since all the vectors are of size m, then all of the bias terms must also be of size m. Next, let's consider what the GRU is trying to do. I think the names are very helpful here. Z of t is the update gate vector, and R of t is the reset gate vector. By the way, if you didn't know, the circle with a dot in it means element-wise multiplication. So 1 minus z of t is an m-size vector, and h of t minus 1 is also an m-size vector. When you multiply these together, you are doing element-wise multiplication. So let's start by looking at z of t. How is it used? We can see that z of t gets multiplied by one term involving x of t and h of t minus 1. Then 1 minus z of t gets multiplied by the previous hidden state h of t minus 1. This is very helpful. You can think of z of t as telling us, what should we do? Should we take this new value for the hidden state, or should we just remember the previous hidden state, h of t minus 1? Why is that helpful? Well, remember what we learned about the vanishing gradient. If we use a simple RNN, it's prone to forgetting things that it's seen in the past. By using this gate, it explicitly allows us to remember the previous hidden state so that the hidden state can be carried forward to the next hidden state. By the way, since z of t is the output of a sigmoid, its values are always between 0 and 1. Therefore, for h of t, we are always taking a weighted sum of the previous h of t minus 1 and this other function. So if z of t is close to 0, then we'll remember the old value, h of t minus 1. But if z of t is close to 1, then we'll take the new value and forget the old h of t minus 1. By the way, you can think of this other function as analogous to what the simple RNN is doing. This is very important, but there's one more piece of the puzzle before we can move on to a helpful interpretation of what's going on. I want you to look very carefully at this equation for z of t. What does this look like to you? Well, it's a sigmoid of some dot products plus a bias term. What does that look like? Well, you might recognize this as exactly like a dense layer. Now you might object, saying that there are two weights, so it's not exactly like a dense layer. But in fact, the way that these units are often implemented, what we do is we concatenate x of t and h of t minus 1 into a single vector. Let's just call it v for short. If we concatenate those inputs and we concatenate the weights, then we just get back to our regular old dense layer, where we have one input multiplied by one weight matrix plus a bias term. In other words, what is this? This is just a neuron. Now, notice that it also ends with a sigmoid. Importantly, this sigmoid is not a hyperparameter. This is usually always a sigmoid because the output is always a number between a 0 and 1. That's how we can take z of t and 1 minus z of t later on in the GRU. So what is this neuron predicting? It's like a binary classifier telling us essentially the probability that we should take the new value for h of t, or if we should keep the old value, h of t minus 1. So if we ignore the reset gate for now, here's how we can interpret the GRU. First, remember that h of t is essentially the weighted sum of two things, h of t minus 1 and the output of a simple RNN. Z of t, the update gate vector, is like an output probability telling us the probability that we should keep the output of the simple RNN. In other words, keep h of t minus 1 with probability 1 minus z of t, and keep the simple RNN output with probability z of t. The final h of t is then just a mixture of these two, allowing us to keep the most important parts of h of t minus 1 and discard the rest. Now, I want to make one small clarification. Please note that this is really for intuition only. These are not really probabilities of keeping and discarding, because we never actually keep or discard. Instead, what we actually do is take a mixture of the two components. For instance, 25% of component 1 and 75% of component 2. But we don't actually keep or discard. In actuality, the word gate is very helpful. Imagine two openings side by side. Now imagine a gate, which is the same size as each opening, but can only slide between the two openings. Thus, it can only fully cover one of the openings at once, or it can simply cover a part of each. But notice that in total, it always covers an area equal in size to one full opening. In other words, if one opening is 25% clear, the other opening will be 75% clear, and they always sum up to 100%. So picture this like an ice cream maker that can give you some mixture of chocolate ice cream and vanilla ice cream. Maybe you like chocolate ice cream more, so you choose 90% chocolate and 10% vanilla, sliding the gate to the appropriate point to achieve this. Note that in practice, this is called a convex combination. You can also think of it like a soft mixture or soft selection. Let's now turn our attention to the other gate vector, the reset gate vector. How does this come into play? Well, first, let's consider how this is calculated. As you can see, it's just another neuron, so that should give you some comfort. There is really nothing new here, as I promised. We're just making use of neurons, which we've already learned about, just neurons connected to more neurons. Now, it's called the reset gate vector, which is a good hint about what it's for. Remember that we called the second part of the h of t calculation a simple RNN, but this wasn't entirely true. This is because this is where the reset gate appears. As you can see, the reset gate is used by doing an element-wise multiplication with h of t minus 1. Importantly, remember that the values of r of t are always between a 0 and 1. What happens if we multiply h of t minus 1 by a value close to 0? Well, it just gets closer to 0. What if we multiply by 1? Then it just stays the same as it was before. In other words, before multiplying by the hidden-to-hidden way, WHH, we decide which parts of h of t minus 1 we want to remember and which parts we want to forget. So we forget them simply by resetting them back to 0, hence the reset gate. Note that this performs a very similar function to the update gate z of t, it's just in a different place. So it's just reinforcing our ability to remember and forget different parts of h of t minus 1. Okay, so to summarize what we've learned so far, what is the GRU and why is it useful? A GRU, first and foremost, has the same API as the simple recurrent unit. The output is still h of t, and it still depends on h of t minus 1 and x of t. The difference between this and the simple recurrent unit is it has functionality for remembering and forgetting what was in h of t minus 1. This solves a problem we had with simple RNNs, where, due to the vanishing gradient problem, it would forget things that it saw earlier in a sequence. We accomplish this by adding little binary classifiers in the form of logistic regression neurons that output a prediction on whether to remember or forget.